freeze that. There we go, finally. Okay, so in the first one, how'd we do? $104? And in the second one, how'd we do there? 108.16, and in the third one, 112.49. You do okay? Okay. Did anybody like try to plug into a formula and solve it that way? You did? All right. So the whole reason I wanted us to warm up with this is I didn't expect you to know the formula or remember it, but I just kind of wanted to go through the steps of the process so that when we do look at the formula, we can kind of see where it comes from, right? So this, I just have it worked out the nice long way. Okay. All right, so before we get into interest rate problems, we are going to start with exponential growth and decay. So if you'll remember last class, when we did our inverse functions at the end, I talked a little bit about the graphs of exponential growth and decay, right? And we talked about on the growth ones, you got this curve that went up like that, and on the decay ones, shrunk down like that. Okay, so we're going to be looking at problems, more like application type problems where the growth and decay mimic this. All right, so starting with growth, right, we're talking about when we start with a certain quantity and it increases by a factor over an interval of time. Right, so when we talk about linear growth, it changes by the same amount each time, right? But this time it changes by a factor, right? So we've got this nice handy dandy formula, which always works with these. Right? We have y is equal to a times, and then quantity 1 plus r raised to the t power. Okay, and so in these, that a represents the amount that you begin with. So the amount initially start with. R represents a rate. And because we're talking about, this is a plus in here, this is a rate of growth for these. And then t is going to be time. And the situations are going to change. Sometimes time will represent years, sometimes it'll represent minutes, sometimes it represents seconds, weeks, it just depends. You always have to read the context of the problem. All right, so we're going to go ahead and jump into a few examples. And again, this is printed for you on that handout that I passed out. So we have the inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. So we want to write an exponential growth function that represents the attendance after t years. So again, the things we want to pay attention to are the fact that it says increases. So when we see that, we know that we are going to have the situation where it's y is equal to a times 1 plus r to the t. All right, so I'm just going to identify the pieces that we have here. We've got 150,000 here. And again, inaugural attendance, so that is the beginning amount, the initial. So we can say A is equal to 150,000. And then it tells us the rate is 8%, and we're going to convert that to a decimal. So R is equal to 0.08. Right, and then writing the exponential growth function, we can put this as y is equal to 150,000 times 1 plus 0.08 raised to the t. And we can go ahead and simplify by adding that 1 in the 0.08. So we get 150,000 times 1.08 raised to the t power. And you can leave it as y, or this is a function in terms of time. We can also come back over here and turn it into a function. Use function notation, again, in terms of t, in terms of time. So once we have established the equation that represents the growth, now it becomes a lot easier to answer when it's asking about what happens in this amount of time. So in B, it says how many people will attend the festival in the 5th year, and then round your answer to the nearest 1,000. All right. So in the 5th year, that means when t is equal to 5. So I'm going to solve f of 5. So 150,000 times 1.08 raised to the 5th power. Again, these will all be calculator problems. We don't expect you to do any of this by hand. Just be careful of your order of operations. What is the 5th power on? It's only on the 1.08. Okay, and we can plug this into the calculator in one step. All right, so I'll do the 150,000 times 1.08 raised to the 5th power. Let me hit enter. Okay, so we've got 22399.2. So this is 220,399.2. But then it says to round our answer to the nearest 1,000. So what's the nearest 1,000 for this? The thousandths place is where? Where the, yes, this term here. So what's the closest 1,000? 220,000. Right. So we have about 220,000 people or attendees in the 5th year. All right. So for the next part, it says during what year will the population reach 450,000? So what is our unknown now? The t is the unknown, okay? And so the 450,000, that is the outcome, or the y. And so what we're going to do is plug that in for our f of t, or y. So we get 450,000 is equal to 150,000 times 1.08 raised to the t power. Okay, so we don't yet have the algebraic tools to solve for the t. And so we are going to use graphing methods to figure out what t is. Alrighty, so if we've got a y is equal to 450,000, that's really grand scale on a calculator. But what do we notice about 450,000, 150,000? Yeah, we can reduce them. So I'm not going to divide out the 150,000. I want to go ahead and keep it, but I am going to reduce. They both can be divided by 10,000. So we can simplify this side to 45 is equal to 15 times 1.08 to the t power. Okay. And that'll just reduce the scale so that when we go to graph this, we don't have to adjust the window so much. All right. So in your graphing calculator, we'll go to y equals, and on one side of the equation, we have 45. So I'm going to put 45 there. And on the other side of the equation, I've got 15 times 1.08. And we're going to raise it to, now keep in mind our graphing calculators can only read x when we're graphing, and so instead of t we're going to use the x variable here. Okay, and hit enter. Okay, the other thing I want to pay attention to is the window, because if you just do a standard window, it's going to go from like -10 to +10 on the x. But we're not really interested in -10, right? We're not talking about, so again, what does the x represent in this function? Time. So we're not really talking about negative time in this one. We're talking about moving forward. So I'm going to start my window at -1 just so that I can see the axes. And for the x, how far to the right do you think we need to go? We saw here that when time was 5 years, we hit 220,000. So how far over do you think we should go so that we'll hit that 45 or 450? You want to try 14 years? Sure. And do you have to get it right the first time? No, you can always adjust it. Okay, so let's go down here on my y scale again. I'm going to start it at -1 again, just so that I can see my axis there. And for my maximum, I've got y equals 45. So I need to go past that. So I'm going to go ahead and try 55. That should go past. All right, and then we'll hit graph. And watch it go. Oh, did we make it? We're barely on the edge, so no big deal. I'm going to go to my window. I'm going to adjust this to, let's just go, we'll move that to 20. Try that, and that should go ahead and get a much clearer image. Because what is it are we looking for in this image? We're looking for the intersection of them. Where do they intersect? Okay, so now we can hit second trace. That takes us to calculate. Scroll down 5 to intersect. Hit enter. And then it's going to ask you, is this the first curve? So we'll hit enter for yes. Now it's on the next one. Is this the second curve? Yes. And then it's saying, do you want me to guess now? So hit enter again. And there it goes. Okay. So it has the intersection there. All right. So what do we see as the x value of our intersection? 14.27. Okay, so I'm going to say t is approximately 14.27. And that represents what unit again? Years. Okay, so I am going to ask when you solve these graphically that you do put a sketch in. And it doesn't need to be a perfect sketch here. So I'm just going to do this, and I'm going to do this, and I'm just going to label. This is my y equals 45. This one is my y equals 15 times 1.08 to the x power. And again, we found the intersection here. Okay. So it says t is equal to 14.27. Did we have a starting year on this one? No, we didn't. So this is about the 14th year. So population reaches 450,000 in the 14th year. Okay. Any questions on what we did there? Okay. Here's our next example. In 2012, you bought a sculpture for $380. Each year, T, the value V of the sculpture increases by 8%. So again, the words to pay attention to are, we see increases here. Okay. Right. And so since it's changing by a factor of 8, we know that we are going to use a growth equation. So again, it's A times 1 plus R to the T. All right. What's our A value in this case? 380. And what is our R? 0.08. Okay, it's actually telling us to call this value of v here. So our exponential function will look like v, and again I'm going to put it in function notation in terms of time is equal to 380 times 1 plus 0.08 to the t power. And again we can simplify that to 380 times 1.08 to the t power. Okay, so now we have the equation that models the growth. So in B it says, what is the value of the sculpture in 2016? So what's different in this one? Okay, so we started in 2012. So if we're talking about 2016, time is 4, yes. So in this one, we're going to say time is equal to 4 years. And then we're just going to plug it in. The value in 4 years is equal to 380 times 1.08 to the, oops, no longer t, we're replacing t with 4. Okay. Anybody plug that in already? $516 and what? 0.9. We'll round that 0.99. $516.99. All right, and then in C, when will the value of the sculpture reach 6,000? So again, what do we have to do for this one? We're going to have to graph. Okay, I'm going to give you guys a second to graph that on your own. Okay, so there's our graph. What was our intersection? 35. 35 point, it came up to like something. 35.9, something like that. 0.85. Okay. Okay. So again, what does that represent? Years. Years. So it's about 35.9 years later when the sculpture will reach a value of $6,000. But the question is, when will that occur? So we can say in, oh, this is so sensitive. There we go. Okay. So in the 35th year, or again, when was the beginning point of this function? It started in 2012, so we'd have to do 2012 plus 35. Right. So that would be in 2047 or in 2047. Okay. Yes, City. Yes.
Because it's 35.9, that's mm-hmm. Not even 35 years after, and then it's the 0.9 of the next year.
Yeah. So well, it didn't quite get there. So, well, let's see. How do you want to think about this?
Because if 35 years, it's 35.9, then 35 years are done, and then it's
35 years are done. Oh, that's a small technicality. I guess it depends on how you think about it. Yeah, if you say 35.9, then it is the following year. Small technicality. I guess it depends on how you want to think about it. I'm not going to get picky on that one.
Okay, so is it okay
yeah.
if I say 2048?
2048? Yes, that would have been fine. Yes.
Will it ever give like the month?
No.
Okay.
Not usually. I mean, unless you had something that the equation was done monthly, but yeah. But usually it doesn't. Okay, so now let's look at exponential decay. So difference here being that we are now decreasing by the same factor over time. So what changed in this little formula?
It's minus.
It's just minus, okay? Everything else stays the same. A is still the amount that you initially began with. Okay. R is still the rate, but in this case it's subtraction, so we'd say it is a rate of decay. Or you could say decline, same thing. And T is still time. And again, you'll have to pay attention to the context of the problem, because it could be years, could be months, could be days, seconds. Yes? Yeah. Okay. So here is a real life example that's really depressing.
Oh.
Yes, cars. Nothing loses value faster than a car. Okay. And a lot of you guys will probably be driving in the next year. Yes?
Yep.
Yep, not you.
I'm gonna.
Okay. All right. So you'll see, right? You're gonna get your first car, and then down the road you're gonna go to trade it in, and they're gonna offer you no money for it, and you're gonna be like, I don't understand, right? But yeah. Okay. So you buy a new car for $24,000. The value of that car decreases by 16% each year. And yes, it truly does. It's really sad. Yeah. Okay, so again, things we want to pay attention to is that it says it is decreasing, and then again, it's by a factor here. All right, so again, that tells you that this is going to be an exponential decay. So it's just 1 minus r. Okay, and everything else is the same. All right, so identifying the pieces. What is our A value this time? 24,000. And our R is, what will our R be? 16%. So we'd have to turn that into 0.16. Okay, and then it's just going to become a plug this in. So y, or again, this is a function of time, is equal to 24,000 times 1 minus 0.16 to the t power. And again, we can simplify it to 24,000 times 0.84 to the t. Right. So basically, each year, the car is worth only 84% of what it was worth the year before. I had a friend once, he bought a brand new car, and after a week decided he didn't really like it, so then he went to take it back, and in that week that he drove it, he lost, guess how much money? $5,000.
What?
Nope.
In a week?
In a week, yeah.
Wait, in a week?
How does that change?
Is it like that take a
Was it like brand new at first?
Yes, it was brand new, and
How much
then
did he drive it?
not much.
Oh my god.
He only had it a week. I mean,
So wait, what happened, sorry?
that's how fast cars decrease in value. Once it goes from what's considered new to used, yes, it's really depressing. Okay. Okay, so let's determine the value of the car after 2 years. All right, so we are looking at f of 2. So 24,000 times 0.84 raised to the second power. Okay, anybody plug that in already?
Yeah.
All right, what'd you get?
1,934.
40 cents. Look at that. How much depreciation was that?
A lot.
Yeah. Mm-hmm. Okay. Estimate when the car will have a value of $12,000. So what are we solving for here? The T. So again, we're looking at $12,000 is equal to $24,000 times 0.84 to the T. Again, you can reduce this to help your graphing window. We can divide out 1,000 in each, so we can have 12 is equal to 24. And again, that'll just help your window. All right, so pulling up. Okay, so y equals, I changed this one to 12 and this one to 24 times, this will be 0.84, and let me just delete that one. Okay. All right, adjusting my window. Again, I started at -1. What's a good y value, you think? Or, sorry, x value to the right. How many years out do you want to go? So it took 2 years to go to 16,900. And where, you want to try 5 years? Okay. And how about my y? Where should I go up to? 15. That sounds good. All right. And let's see if we capture the intersection here. Ah, we got it. What changed in this graph? It's down. Okay. All right. So again, when you solve these graphically, I do expect to see you sketch the graph in. And you'll see my graph is not very nice, but again, just looking for a sketch to show that you did indeed sketch it. Y is equal to 12 here. This one is y is equal to 24 times 0.84 to the x. And again, we're looking for that intersection, which I neglected to look at because I just started drawing. Okay. And so, second trace. Find the intersection. That's the first curve. Second curve. Yes, take a guess. And there we go. So we came out to what? 3.98. Okay. All right, so this is, x is about 3.98. All right, so we can say in about 4 years, the value will be $12,000, which means basically what happened in the 4 years, it decreased by half. Yes. Okay, any questions on what we did? No? All right, so now we're going to look at compound interest, which is more similar to the warm-up problem that I gave you. What's that? Yes, compound interest, which is what we did. So interest on interest, right? So in that first year, remember we started with $100 and then we earned $4. So on the next year, we weren't earning interest on the $100 still. We were then earning interest on $104. Okay. So there's a little bit more involved. And so this formula, it's a little bit longer. So y equals p times 1 plus r over n raised to the nt. And we often will see this instead of y, but we'll see this as a of t, as in what is the amount you will have after some amount of time. Okay, So the P here is just like the A in our exponential growth and decay problems, except because it's money, we call it principal. So the principal, but again, it is the initial amount. So that's the money that you start with. R doesn't change, it's still a rate. In this case, it's a rate of interest. Okay. When we're doing compound interest money problems, T is still time, but the time is in years. And then the N, this will be the new part. The N is the number of times compounded in 1 year. So how many times will they add interest onto your earned interest in 1 year? Okay, so in the warm-up, I only said annually, right? So when we talk about this, we put compounded annually. So annually means 1 time per year. So annually means N is equal to 1. Okay. What if I said quarterly? 4. What if I said every 3 months? 4. Okay. What if we did monthly? What is N? All right. What if we went to weekly?
57.
And how about daily? 300. Is it 65? 365? Okay. Unless it's a leap year. That's right. That's this year.
Wait, so there's a leap year?
Yes.
That's so fun.
Yeah,
Someone gets to have their birthday.
I'm on the verge of like Gemini, like Cancer, because I'm June 21st. So I don't know.
Oh, does it change? I didn't realize that.
Yeah.
Okay.
It does.
I'm on the verge of Virgo and Libra, but I thought I was always. I'm a Leo. Am I such a Leo? You're such a Leo.
Okay. So let's look at our first compounding interest problem. Okay, so you deposit $100 in a savings account. What does that $100 represent? Initial amount, which is the P. P is 100. Okay. In an account that earns 6% interest, so that 6% is the rate. So R is equal to, and we'll convert that to decimal, 0.06. And then it says compounded monthly. So that means N is equal to 12. All right, so this is just a matter of plugging in, because it says write a function that represents the balance after T years. So again, how much money? What is the amount of money we will have in some amount of time? So principal, $100, times 1 plus R is 0.06 over N is 12, raised to 12 times T. So there's the equation that will answer that question. And then it says, how much money will you have in the account after 10 years? So what do we have to do there?
Plug in 10.
Plug in 10 for T. So we get A of 10 is equal to 100. 1 plus 0.06 over 12. And this would become 12 times 10. Okay, so you can put this all into your calculator in one step. Just be careful of parentheses. Right, so we have 100 times, and then I've got 1 plus, and we would have to put parentheses around the 0.06 over 12, unless you have a built-in fraction bar in your calculator, which actually probably most of you do have. Okay. All right. I still have to close the outer parentheses, and then this is being raised to the 12 times 10 is 120, and hit enter. All right. How much money do we have in 10 years? And rounding up, so this is about $181.94 in 10 years. Okay. All right. Any questions on what we did on that one? Okay. I'm going to let you guys work this one.
Is that like a pyramid scheme?
Is this what?
Like a pyramid scheme?
It is? No, it's just the companies often contribute to, you'd say, like your retirement account. Yes. Yeah. Okay. And then the only thing I'm going to ask you here is to pay attention to what the question is actually asking at the end. Okay. Yes?
Slime.
Okay.
Honestly, yeah.
So hopefully you did come up with this amount, but then what needs to happen?
You have to subtract the 1,000.
You have to subtract the 1,000. Okay, so then minus the $1,000 that you put in, and that means how much did your company invest?
$485.95. Why would the company do that? Why would they give you money?
It's incentives.
Because they want you to work there.
Yes.
It's just like how like some companies offer like insurance in some sort.
Yes. These are important things.
Wait, so what's that only important?
Except you guys are actually covered under your parent insurance till you're 26.
Oh, I'm 26.
Yep.
That's so old.
I feel like I'll have my life figured out by then.
Is that the Gerber
Is
that what that is?
Okay.
Oh my god, that's so funny.
Okay, that sounds terrible.
That's
Okay.
So bad.
Last example. We have a certain bacteria culture that increases at the rate of 4% per minute. Okay. At 6 a.m., there were 150 bacteria in the culture. Okay, what kind of problem have we gone to?
Exponential growth.
Exponential growth. Okay. So again, we see increases here. So we know this is an exponential growth. So y is equal to a times 1 plus r to the t power. What is t being represented by here? Minutes, yes. So t, again, it is in time. It is time, but in minutes. What's our rate?
0.04.
0.04. Okay. So we're just going to plug all this in so that we model the situation here. So y is equal to, we started with 150,000 bacteria at 6 a.m. So 1 plus 0.04 raised to the t. Okay. So again, t equals 0 is 6 a.m. Alrighty. In B, it's asking, though, how many bacteria were present in the culture at 5:45 a.m.? Negative 15, exactly. So we're actually looking back in time here. Question? Yeah. Okay. So y is equal to 150,000. And I didn't simplify my equation earlier. I'm going to go ahead and simplify this to 1.04. And this is going to be raised to the negative 15 minutes. Anybody calculate that already? What do we get?
83,289.68.
Okay. 68 bacteria. Does sound like a lot, doesn't it?
That wrote a lot in 15 minutes.
Mm-hmm.
That was fun.
Okay. All right, so we went negative time there. And now the next question is, at what time were there about 90,000 bacteria present? What do we have to do here?
Plug in 90,000 for Y.
For Y. So 90,000 equals 150,000 and 1.04 raised to T. All right, again, just for simplifying and making your window a little bit smaller, we can reduce. Let me see, we've got those we can divide out and divide out. So we can actually turn this into 9 equals 15 times 1.04 T. Okay, if we're starting with an initial amount of 150,000 and we're trying to figure out the time at 90, where are we going in our window?
Back.
Yeah, we're actually going back. Okay, so again, here I've got Y equals 9. Let me delete the 2. Okay, and then over here I have 15 times, this will be 1.04 raised to the X power. Oops, let me delete that one. Delete, delete, delete. There we go. Okay, so on my window, I'm going to go further back in time. How far back do we want to go? We'll try negative 20. All right, so we'll do negative 20. And I can go to positive 5. That's fine. How about Y?
Negative 15.
Okay. Actually, do we need to go to negative Y?
Oh, wait.
No, don't need to, but how high up do we need to go? At least 9. 15, that covers it. I think I'm happy with that. Okay. All right. Okay, we found the intersection. So again, second trace, intersect. First curve, yes. Second curve, yes. Take a guess. There we go. All right. What is our X value? About negative 13. All right, so again, if you're solving these graphically, which is the only method we know for now, again, make sure that you do a sketch here. And we've got something like that. Again, that's our Y equals 9. This one is our, whoops, that was supposed to be a Y, not a 9 again. Y is equal to 15 times 1.04 to the X. And we found that this was approximately negative 13. Okay, so again, what does that negative 13 represent?
13 minutes.
13 minutes
Before 6
before 6 a.m., which is what time?
5:47
Yes, before 6 a.m. So this is about 5:47 a.m. We had 90,000 bacteria. Okay, what do we think of this? Good? Okay.